hit the record button. Wonderful. Okay, then we'll start again just for the recording. So thank you so much for having me. Today I want to talk about, the title is on the autoregressive neural emulation for PDEs. It is partially based on a work I published last year at NeurIPS, which is on a PDE emulation benchmark suite, but I extended this to include some personal perspectives on the topics and of course to dive into some of the results in greater detail. I'm a PhD student with Professor Turi at the Technical University of Munich. Okay, so my talk is going to be, let's see, well, not working yet. Let me switch. Okay. Okay, cool. So I'm going to talk about the simulation emulation of spatial temporal problems, and I thought I started with some nice teaser figures that I also presented with the benchmark paper. So I have problems that reside in 1D, 2D, and 3D, and have an additional time dimension to them. So here you have some nice teaser problems that eventually also appeared in the benchmark suite. Roughly the agenda for my talk is I will first talk a bit more of classical approaches to simulating time-dependent problems, and then introduce aspects where neural approaches could come in. Then specifically I will talk about autoregressive neural emulators, and specifically also how they are going to be trained. And then I will talk a bit about APEBench and how my perspectives on designing a benchmark suite for PDE emulation. And then in the end we look at some specific results, and in particular what I want to talk are some insights and parallels between emulators and simulators, and I want to share some of those with them. I would say the first third or fourth of the talk is going to be a bit more high level, but then it's getting gradually more into detail, and as Victor said, feel free to interrupt me at any point and we can discuss on that. Okay, cool. Let's get started. As said, I want to start very high level, very broad on simulating time-dependent problems. So how would you do that on a super high level? So typically the problems we are interested in are described by continuous models, oftentimes partial differential equations. So here I chose probably the simplest one you can have, a one-dimensional advection equation. If you want to solve that problem, well, you would apply some simulation technique, oftentimes involving a symbolic manipulation of the PDE, and eventually also an implementation on a computer. And I want to abstract the classical simulator that solves PDEs with this calligraphic P. And specifically, we are interested in time-dependent problems, so we need a point to kickstart a simulation. So for instance, we need an initial condition, which for instance could be a collection of superimposed sine waves, which we also discretize, so we choose a representation for that. In the easiest case, in 1D, just some equidistant grid, and then are able to discretize this initial state. Then how do we obtain a trajectory? Well, we use our initial state here. I now have a color coding instead of basically have it displayed on the y-axis. We apply our simulator, go to the next step, and then essentially we can apply the simulator again, go to the next step, and so on and so forth. And essentially we're not just interested in a handful of steps, often hundreds, thousands, 10,000s of steps, so that continues on and on and on. And essentially we see that there are some spatial temporal patterns that emerge. We can present this a bit differently, and then essentially we end up with some spatial temporal plots. So here we have a time and a space axis. So essentially also what I showed you in the teaser. Okay, so this is a bit high-level overview of classical simulation. So then when we simulate problems, or I think simulation or numerical analysis, you might also say, is the art of making a compromise. Because essentially we know that we will eventually make an error when we simulate those problems. So on the one hand, we want to, of course, be as accurate as possible, but we also know the more accurate we go, the more computationally expensive it becomes to obtain solutions. So typically, when we assess simulation techniques, we have a trade-off between speed and accuracy. And in a sense, if we wanted to see this a bit more formally, we could have, if we wanted to find a method which is optimal, we would eventually see a Pareto frontier in there. So there are simulation techniques which are slow, so they might be left on the speed axis, but highly accurate. Typically, those problems are the ones described by classical numerical simulators. So this is a bit broad. I'll give you an example in a second, but at least to position them in there, that's what they're known for. They're trusted, sufficiently accurate, or oftentimes also very accurate, but also quite slow. And then typically the bottom right is made up of reduced order models, which is of course a big term that can incorporate a lot of things. Give you some examples. So in the top left, we could have the classical legacy Fortran code, which runs a single core, higher order FEM method that produces a high resolution, accurate or highly accurate solution, but of course is very slow. On the mid, we could find something which maybe is based on modern hardware accelerators like GPUs, so a CUDA-based implementation of a finite difference or spectral method on a uniform grid. And in the bottom right, you might have something which is a classical reduced order model technique like a POD or PCA with highly reduced degrees of freedom and then maybe executed on very specialized hardware. So you go like very fast but decently inaccurate. And of course, this also highlights an important aspect here. So it's not just about the technique itself, it's also about the implementation, of course. And now where does neural approaches come in? Of course, the idea with any kind of method development, it's not just with neural approaches, I guess it's also with classical approaches, is that we want to push the Pareto frontier. So we want to find something which is not just here, but which essentially moves the Pareto frontier. And then there are, of course, like multiple ways to do that. So I would say that a lot of research in classical simulation is, of course, to push the classical numerical solvers, to make them more accurate. Of course, in the best case, not sacrifice speed, but sometimes we're also fine with sacrificing speed if we get even more accurate than what is the status quo. What is the other way we can push the Pareto frontier? It's in the bottom right. So we can, for instance, find something, does it work? Yeah. For instance, find something which goes faster and maybe is a bit more accurate, which keeps the level of accuracy but goes faster. Or if we are crazy, we could say, well, be even more inaccurate, but if you are faster, that would be very nice. Okay, so this is where neural approaches come in. My personal perspective is that they are best suited for the bottom right approach. So neural networks, based on the way we train them, based on the way they're defined, they might not be the best fit for up here. There could be some ways we could integrate them to move the Pareto frontier here, but I guess this is a regime where they have a very good fit, or where we could make a lot of progress with them. Okay, so that's where I see the neural approaches, but what kind of neural approaches are out there? And this I also want to keep like very high level, but what could we do? So I guess most prominent approach is of course to use physics-informed neural networks. I think this is the term which got the biggest popularity over the past years. So essentially we train networks to become the continuous solution function to PDEs, which is a bit in a contrast to what we typically have with numerical methods. So there's not necessarily the idea of discretization involved. They are, of course, very interesting, technically and scientifically very interesting, but I think so far their practical relevance is limited to some, I would say, more abstract problems, like high-dimensional PDEs or specific inverse problems, but not necessarily these engineering problems which are in 2D, 3D plus time. What is another approach? So we could have smaller components to model stuff within classical simulation pipelines that are heuristic anyway. So for instance, this could be a multi-scale model. So instead of having a simple turbulence closure model, have something more sophisticated that uses like a medium-sized neural network trained on experimental or simulation data, and that I think is also has been quite successful. And I think this is also the one where we might be able to push the Pareto frontier in the top left. This can also be done in numerics. There have also been some successful approaches to model heuristic points in numerics, for instance, like for flux limiters or step size controllers, but it's not the thing I want to talk about today. Then another approach would be to augment existing solvers with neural components. So we in our research group like to call this correction or a solver in the loop approach, but I already talked with Emmanuel about that. So I think there's probably many names for this, but this is an interesting approach because we have the neural networks operate on a state discrete level, which is a different way they could act than in the different ones, but we still keep the existing knowledge from numeric analysis. The most bold approach, and the one that I want to talk about, is to fully replace the numerical solver. with a neural network. Of course, you might ask why. I'll talk about it in a second, but I think a high-level why could also be, deep learning by itself is, of course, trying to be a bit ambitious, so, well, why not be ambitious on that? Of course, there might be other ways to do it as well. It's just like to give a high-level overview here. Okay, talking about why we should replace the numerical solver. So I think the most idealistic and practically relevant reason to do this is to find something more efficient, so something that truly pushes the Pareto frontier, very likely only in the bottom right. Of course, this is very tough, and I think if you put like very strict mathematical scrutiny on that, that is actually very tough to achieve. But it's still ambitious, and some research showed that it actually holds and has some promise on that. Then there is the other idea that I think is also super interesting, the idea of imitation learning. What do I mean by that? And essentially we find the idea of replacing numerical solvers with deep learning as a way to bring existing solvers which exist in other implementations. So for instance, which exist as this Fortran code I told you about, or which exists on implementations which cannot run on other hardware. First of all, we bring them on modern accelerators like GPUs or other kind of accelerators, and they can already gain a lot of benefit by just being on that hardware. Or we also want to have them in modern deep learning frameworks to then allow them to be used for other downstream applications, which would be harder if we had the legacy solvers, because then we had an interface problem. And moreover, if we did that, we also gain the advantage of features that we have in deep learning frameworks, like differentiability and vectorized execution, which some legacy solvers lack or do not natively support.
But
yes, sure.
In imitation learning, you could stand to lose some interesting features of the legacy solver, because the legacy solver uses a numerical method which has been proven to have some properties, convergence, consistency, conservation, whatever, yeah, which you lose when you go to the imitation learning. So do you know whether there is work on trying to, because it's actually a super interesting idea, right? You have something that runs on a CPU, you want to import it on a GPU, super easy using the network, but are you aware of work that is able to do that while still trying to get some properties of the legacy solver?
I think the idea of like getting these properties is then a bit detached from whether we do it because of imitation learning or because whether we want to find something more efficient. And I guess there is definitely work. I don't have probably have to look into my citation base, but I mean, in the end, if you include any structural biases into the network, you might have certain properties by construction, some ideas to conserve certain quantities. So that might be a way to get those, but I think the anecdotal evidence is often that the more you constrain the network, the harder the optimization problem becomes eventually. And of course, the more you constrain it, the more you constrain it, the more you constrain it, the more you end up being the numerical method again, which is good. I think it's desirable, but it's also maybe not what you would want if you used the neural approach.
You still port it to GPU, so that's already nice.
I
understand.
Yeah. So the more inductive, more structural biases, the harder the optimization problem, the closer we are to the numerical method. So the slower the speed up becomes due to going to a different method, but we might still have the benefit of being on the GPU. And I would say this imitation learning is a bit of the poor man's approach to go to the GPU. I think the structured approach would of course be to invest the human labor and write code for the GPU natively. But seeing at how much human labor went into writing the Fortran code, that's of course quite a significant effort. Okay. Okay, then I have one last point, and I guess this is also going to be a bit of the theme of my presentation. So what I'm going to show you later is not something which necessarily is more efficient. Very likely it is not. It's also not something which was based on the motivation to imitate, because I already have a very efficient solver on a GPU, so why learn the network? So I guess the motivation of what I'm doing is mostly science, right? Understanding something. So I find this learning process very interesting, and seeing intricate similarities and differences between emulators and simulators. And I kind of put this in quotation marks here, but I find it interesting that when we train these emulators and we see what kind of constraints they get up we see that this is like kind of a way of automating numeric analysis. That's of course like extremely bold. Like this can of course be considered offensive. But if you think about it, that if you have training of many different deep learning paradigms also in natural language, we do have some emergent abilities that come up within these neural networks, and we do also have some emergent abilities within these emulators, and they just come up purely based on a data-driven learning process. Might they be due to the data, might they be due to the inductive bias of the network or something else? That of course remains to be discussed, but at least this is something I find very interesting. And lastly, I have a point which is also not something is guiding the presentation, but I think pragmatically one could also say that a data-based approach is a way to combine different data modalities. That could be more relevant for practice because I think what I'm going to present you now is purely based on synthetic data. Okay, so this is a bit of a high-level perspective. Maybe I could motivate you why I find that interesting. And now I want to talk about autoregressive emulators. So we could have now emulators for stationary problems, but well, let's be bold and look at the time-dependent problems which tend to have some intricate difficulties to them. So let's recall again the setup we had before with the autoregressive rollout of an existing numerical solver. So where we essentially autoregressively applied a method, which is also what happens if you do any kind of time-stepping ODE integration, right? And we got our very long trajectory. And essentially now what we're interested in is approximating the behavior of the simulator. So we want to train a network to replace the simulator. So loosely speaking, to have it approximately equal to the numerical simulator. So how can we do that? So the most intuitive, or I think the first thing that could come up with is that we have it be in the same format as the numerical simulator. In terms of something you find typically in reinforcement learning, you would call it first order Markovian. So basically that means it predicts from one time step to the next. So also very much what your numerical simulator does. But there are of course way other options to do that. You could for instance have a non-Markovian setup, similar to what you would have if you had Adams threshold methods, right? You could have an approach which predicted multiple states at the same time. Probably also a lot of names for that. In the literature that I'm reading, that's typically called temporal bundling or chunk prediction, but I guess there are also numeric analysis term for that, I suppose. And there is also the idea maybe, well, predict the entire trajectory, which is, I guess, the most bold thing one can do. Which of the ones shall we choose? I want to give some arguments for all of them. So for the first one, why we should choose a non-Markovian approach is that you can motivate it, like there are also numerical methods which are non-Markovian. When I learned about numerical methods, I was always told they are harder to analyze, that's why we don't like them that much, but I only had like 2 courses on numeric analysis, so take this with a grain of salt. There's also this quite famous Moritz-Zwanzig formalism, which essentially argues that we do need history to some extent because under limited observation, physics becomes non-Markovian anymore. I will talk more about that in a second. Motivation for the chunk prediction could be, for instance, that we have some efficiency, or it might also be an inductive bias for the prediction to be long-term accurate. For the full trajectory prediction, I find it like when I first heard about that, I thought this is like why should you predict the full trajectory? I think we should use the inductive bias that time is sequential, so that should also be how we design our emulators. But then I learned that video diffusion models, which I guess you might have seen, like these VO2 or Sora from the big AI companies, what they essentially do is they don't create the video frame by frame, they create the video at once. So basically when you have a diffusion process over an image, right, this is like an iterative denoising of the image, they essentially iteratively denoise the entire video. So they have a good argument for making an entire spatial temporal prediction at once. So I guess that also motivates why people are now looking into that. One could argue that maybe by having the network predict the entire trajectory, it could learn some internal dynamics which shortcuts integration and might be more amenable to having stable trajectory prediction, but I think that's up to be debated. What I'm going to talk about is the first order Markovian approach, because I believe, first of all, it's simplistic. And I would say that most physics behaved first order Markovian. But as said, this Moritz-20-Formalism, this is something very interesting. And just recently at IK 2025, there was a paper that investigated this very question: should these time-dependent emulators use history or not? And they also base it around the Moritz-20-Formalism. In fairness, I mean, the Moritz-20-Formalism is always used as a bit of a hand-waving motivation. And what they essentially found is that memory is helpful if our states are spectrally limited. So basically that means if they are not fully spectrally resolved. And they basically analyzed by how much the states are spectrally resolved and then by how much memory actually helps in the neural emulators. And they found that it does help, but to be fair, in the cases where it helped, it needed to have, the spectrum needed to be quite truncated. So I would actually flip the conclusion and say for many applications where this is not the case, the first order Markovian is more than fine. So that also motivates me to continue on that part. Okay. So now I hope I could maybe convince you that emulators are something interesting. And now when we have time-dependent problems, well, maybe you also find that first-order Markovian emulators are the way to go. Then now the question is, of course, how do we train them? And so we return to the setting of having the trajectory that was created by a classical numerical method of before. And then, of course, when we train deep learning models, we need quite a large amount of data. So we not only have one trajectory, so we have another trajectory, which is basically the same advection dynamics here, but with a different initial condition. And we could not just have two, maybe we have three, or we have a lot more. So we have a lot of trajectories. And based on these many trajectories, how do we train the first order Markovian emulator? So let's, for the sake of simplicity, say we only have three trajectories. And then essentially, we choose out of the trajectories randomly across the trajectory and randomly across time 2 frames, or basically 2 consecutive frames. So here for that example, I chose 2 windows basically from the rear trajectory and then 1 from the other trajectories each. And then essentially we can split them into an input and a target, and then we essentially have a very classical supervised deep learning problem. We take the input, push it through the network, which I will talk about in a second what that network could be. I just highlighted the prediction of the network here by just some random colors, and we compute a loss metric between the prediction and the reference. Then we have a parameter space and can backpropagate, and then iteratively we optimize the weights of that. So we train the network to, on average, predict across trajectories, across time, from one state to the next. And that is interesting, because you might say that this creates a discrepancy. We have a one-step training, so we train across the state space, given by time or given by trajectory, but only for one frame into the future. But our evaluation would, of course, be very long autoregressive rollout, because that's what we want to do. That's what the simulator does. So that pops up questions of long-term accuracy, long-term stability, or in general, I like to call this temporal generalization. So this is something I find very interesting. And the question, the interesting observation for me was, when I started working on those, is that despite the one-step training, these autoregressive emulators do quite well. So I want to show an animation to you which animates the optimization process of an autoregressive emulator. It's very oscillatory, it will stabilize in a second. So essentially in the top you see the training loss, which is the one-step prediction error. Then in the center you see an inference rollout, which is essentially using the network on an unseen initial condition. And in the bottom you see an error rollout, which will become very important in a second as well. So basically this shows us what is the error we're doing after a certain number of time steps. I will run this animation again. And essentially you see the network does quite well towards the end during the midst of the optimization. It's very oscillatory. And then eventually towards the end of the training it stabilizes. And it is, like, at least from a visual inspection, a decently low prediction of the advection problem over the 200 time steps. Yes, exactly. And this is something I find extremely interesting. So we train on one-step prediction, but still get the autoregressive accuracy, autoregressive stability. Exactly. Okay. The next point I want to talk about is essentially how can we design a benchmark speed around that? Because now we basically have a setting. So we say we are interested in emulators. Okay, we want to have first-order Markovian emulators, and let's also say we want to train them on one-step supervised learning. And now we want to gain insights into the learning process. So we now need to consider the scenario we want to test for different PDEs, not just the very simple advection problem I displayed to you. We want to test different architectures and then gain insights from that. How do we do that? So in that case, we would build some problems or do some experiments, and that's what I designed APEBench for, like how I designed a benchmark suite around that. And I want to walk you through how one could decide a benchmark suite, and I guess how most benchmark suites are set up. So you start at a PDE, so in that case it could be an advection equation. You start at a distribution over potential initial conditions. You make the aforementioned discretization. So you could have some implementation of a numerical simulation. You have a discretization of your initial state. You autoregressively roll out the solver to produce a trajectory, and basically repeat that a couple of times, different PDEs, different initial conditions, and create data sets. These data sets then essentially form the core part of like data sets and benchmark publication. And essentially, you can split your data trajectories into a train part, use some architecture, initialize the network, have an objective like our one-step prediction, train the network iteratively in a classical deep learning fashion, use your trained artifact on a holdout test data set with some metric, and roll it out over time. So far, so good. This is essentially how probably most of the PDE benchmarks are set up. You would find some more simplistic problems like we have with APEBench, or something more sophisticated on unstructured geometries, very difficult PDE dynamics. What I think is special about APEBench is that, I mean, we do look at simple problems, but But I think the one big difference to other PDE benchmark suites is that we deeply integrate an efficient numerical simulation method into the benchmark suite. That basically means we can procedurally regenerate the training data. So, of course, that is a bit of a simple situation, right? You would want to use emulators for settings where training data or data generation is hard, because that's where you hope to get some efficiency boost out of that. But here we specifically choose a scenario concretely on uniform Cartesian grids in 1D, 2D, and 3D under periodic boundary conditions, where we can have very fast numerical solvers, I will talk about in a second, and having them run procedurally gives some pragmatic advantages. So for instance, it reduces the need for data handling, which can become quite tedious with large simulations. And of course, it gives you the freedom to regenerate as much data as you want, and also finely manipulate, or manipulate is of course the wrong word, but like to finely tune what kind of data you want to investigate specific aspects. And one more point I also want to talk about is that we use an ID mechanism to, it's essentially just some reparameterizations on PDE parameters that allows us to more precisely convey what we are essentially simulating and emulating. I want to talk about these two key contributions just briefly. So the fast solver that we're using is essentially a Fourier spectral method. Precisely, it's an ETDRK, that stands for exponential time differencing Runge-Kutta method. So the core idea is that we have PDEs that are in a semi-linear form. That means we have PDEs where the difficulty of integration arises from the linear part and not from the nonlinear part. That, for instance, includes the Kuramoto-Zimoshinsky equation or the Navier-Stokes equation at low Reynolds numbers, but for instance, it does not include strongly hyperbolic problems. So they need to be sufficiently diffusive in that sense to be amenable to a spectral discretization. But if they are, then these ETDRK methods, here I have the first order ETDRK method written down, are extremely efficient. And because they are based on array computations, they work extremely well on GPUs. So the core contribution here is essentially an implementation of the classic ETDRK method from Cox and Matthews. They wrote a seminal paper on them into JAX. And then it comes with all the features of JAX, like automatic differentiation, automatic vectorization, and you generate the data in seconds, so you basically never have to download large data sets. Then the second contribution is these PDE identifiers. So the reason we introduce them is because usually when we have PDE data sets, it is quite hard to say what we are essentially having in them, so like having a really concise descriptor of what these data sets are about. So if we are in this case of the semi-linear PDEs that I mentioned before, that consist here, for instance, of one specific nonlinearity I chose, like the convection term, and then a collection of linear derivatives with the respective coefficients. And you would choose a combination of such. What you would have to convey to uniquely identify the problem would be, of course, the coefficients. You would have to convey the D here, in that case stands for the number of spatial dimensions, the domain size, the resolution points, the time step size, and of course some numerics choices, because obviously your numerics affects the data that's being produced, and potentially there's a good reason to believe that these defects in the simulation also affect the emulation and the training of the networks. So what we did is that we reparameterized that. So essentially we fixed the numerics to a second order ETDRK method under reasonable default settings, which works, I would say, stably and accurately for the range of problems we consider. And then we reformulate the coefficients into something we call a difficulty interface, trademarked name, of course. It is in essence what we get here is these gamma values are stability conditions of the most compact finite difference scheme. That, for instance, means if we have the coefficient of the first derivative in space, which is A, it would be transformed into a gamma, and that would be then the CFL number, because that's the stability condition of the first order upright method. And essentially, this gives these coefficients a nice interpretation, and of course, we reduce the number of parameters. And of course, the nice way is also that these parameters are in reasonably orders of magnitude. So essentially, in order to convey what is being simulated and emulated, you only need a set of parameters and then also the dimension and the resolution. Okay, let's see. Okay, I just have a quick animation to showcase what you can do with that. So essentially, when you say I only have gamma 2 and gamma 3 and the convection nonlinearity being non-zero, setting all the other values to 0, you can smoothly interpolate between different PDE dynamics. So here, let me run that again. So essentially, you interpolate between some diffusion problem, some dispersion problem, the Burgers equation. Of course, simplistic PDEs, but you can adjust the difficulties with respect to specific aspects of the PDE. And this opens up interesting axes of investigation. So the two I want to present to you is first, an investigation with respect to different PDEs. So not just in terms of the class of PDE, or also the specific PDE, like advection, Burgers, etc., but also its concrete parameterization. So for instance, meaning a fast advection, a slow advection, a Burgers where the nonlinear term is stronger or the diffusion term is stronger. Exactly, and then the second axis, potential axis of investigation is the neural architecture. So what we essentially will be using to train our emulator. There are other axes of investigation that I left out for brevity, is that you can of course do different objectives. We only looked at one-step training, but that's the most simplistic one. There might be more training objectives one you could look into. Or you could have different goals in mind. Instead of like fully replacing the numerical simulator, you could use some augmenting strategy. I like to call this neural hybrid approaches, but there are of course different names for that. And then very importantly, when I designed APEBench, which I found extremely important, is to deeply bake in seed statistics, because we want to make like conclusive statements. So we want to do some hypothesis testing, which requires rerunning the experiments under different random seeds to at least make some reasonably good conclusion. And I think this is also a nice feature of APEBench, because when I talked with people about APEBench, I said, okay, this is like 1D PDE problems. Why do you look at 1D PDE problems? They're rather boring. But I didn't say that even if the 1D PDE simulation and emulation is fast, we can use this to our advantage to then parallelize the seed statistics. So instead of then we can fully utilize the GPU with running multiple seeds at the same time, and then essentially not just do one experiment, but do multiple, and then essentially get statistics out of that. So I think that looking at 1D problems can also be quite helpful. Okay, let's look at some results. And the first one I want to look at is a quick refresher on the convolutional network, just to put us on the same page. So from now on, we're going to use these different neural architectures to emulate different PDE problems. And as I said, I just want to quickly refresh a convolutional network. So essentially, what we're going to do is using, for the 1D problems, a convolutional network in 1D. That means we again have our input here. We again have, for simplicity, an advection problem, and want to map that one to the next state in time. So what our problem does is we apply a local convolution. So that means we have our equidistant degrees of freedom in space, and then use, in that case, we use a kernel size of 3. So we use the free neighboring, what is in a region of 3, to predict the next state at this degree of freedom. And then these convolutional neural networks usually have larger hidden representations than on the state they actually operate. So in the advection problem, of course, you have one channel or one, let's say, degree of freedom. In that sense, you might only have the species concentration, and that's also your input and output, but there might be higher dimensional intermediate representations. And then the convolutional network is essentially a stack of multiple convolutions, all with their larger hidden representations and some nonlinear activation. And a very crucial aspect of convolutional networks is that one of receptive field. That means when you have a convolution, that is of course a local operation. It does some weight sharing to be local, and it's a very strong inductive bias. But by being local, it of course cannot see further than the kernel size we give it. That means after one convolution, we only have the receptive field of the that we see in black here. If we do one more convolution, we essentially gain another receptive field. So on a convolution with kernel size 3, we gain one receptive field per direction per convolution. So for instance, if we had like stacked, I think it was 10 or 5, I don't know exactly, convolutions here, you would get the wider orange receptive field. Okay, and now for closing the loop, we're looking again at advection. So now the goal is to emulate the advection equation with a convolutional neural network. And here I essentially have temporal rollout or temporal error plots of the different convolution configurations. So you see in blue basically means it's a convolutional network. And then in the different line styles, I have different depths in convolution. So when we have convolution depth of 0 means we do not have a hidden layer. This is essentially just one linear convolution. Convolution depth of 1 means we have one hidden layer, 2 means 2, and so on and so forth. And then for convolution depth of 0, we have one receptive field per direction, and then essentially for 1 we have 2, and so on and so forth. And essentially what we see here, we look at an advection problem which has difficulty of 0.5, or essentially we solve a problem which is at CFL number 0.5. We see a quite, I think, somehow to be expected insight in that all the networks do work for the problem. Why do we know that it works for the problem? Because their error does not grow exponentially, it grows linearly. But the difference and important insight is that the convolutional networks which have wider receptive field, so in that sense, if we have at least a receptive field of 3 with a convolution depth of 2, work better for the problem. It's an interesting observation, because if you look at convolutional network and they're performing convolutions, this is nothing different than, for instance, finite difference methods are. Finite difference methods are also convolutions. So in a sense, we're using a finite difference method in a deep learning training pipeline to emulate the advection problem. And it turns out that the convolution with, at least a bit of a deeper network tend to work better. Okay. Yes.
If, so it's a good point about the finite difference. Since here you're using advection, right? So you have the exact solution, you can do the exact solution. Where would, for instance, a finite difference scheme for the 1, for the 2, or for the 3 be on this? Of course, it will also depend on the resolution, but where would it fit on this? Where do you think it would fit on this graph here?
It's a good point. You should have added that. I guess it's a bit under that. So I guess it's probably better than the convolution network.
I mean, it depends on the resolution, right? If you put 10 points, it would be bad, but I guess if you put, it depends on the spatial resolution.
Yeah, I guess it definitely depends on the spatial. It's an interesting question. Yeah, I think for these.
I think it would be super interesting to have the curves of, in addition to neural simulators, neural emulators also have the curves for some simulators.
Yeah, absolutely. I do also have some related study we could look at later. It is very interesting. Yeah? I mean, in a sense, this then again raises the question. So here, for instance, the reference data and the training data we again get is based on the spectral method, which for the linear PDEs, so periodic boundary conditions, is exact. And so in that sense, that would be the training data, and that would be the one we test against. But then we have our emulator, but is the emulator actually a good choice? Is of course then dependent on what would be like a very simple other kind of method, like a finite difference method.
Which is not exact, but yes, it's.
Yeah. Okay, so this basically is now one data point. Let us extend the axis of investigation with respect to the parameterization of the advection equation. So essentially now I have 2 more plots. They are still advection equations. The resolution has not changed. So we are here, I didn't say that, but we are at a resolution of 160. And now we have CFL 2.5 and 10.5. And now we go to 2.5, and we do no longer see the zero convolution depth because it has insufficient receptive field, has a very high one-step error, and it also grows exponentially. And so does the dotted line, that's the dotted line, the one which also grows exponentially here because it also is insufficient for this receptive field. It's kind of to be expected, right? I mean, you need a certain receptive field to work under the CFL number because otherwise information travels too quickly. And then we see that the other method, so we have the very deep convolution network that works very well, and we have the one with 2. And the 2 is an interesting case because 2 depth would have a receptive field of 3 per direction, so it should work, and it also does work. The beginning is more or less linear, but then it still diverges, which is because it does have sufficient receptive field, but apparently these convolutional networks need a bit of an overhead to work well, which we also saw earlier where the errors with deeper networks were better.
And if you have 3, does it follow 2? Does it eventually explode as well, or does it just grow linearly?
Good question. I don't have it in mind at the moment. But I think I didn't run 3 actually here. My suspicion would be that it would work like the 10 does for a bit longer, but then might also diverge. I think it's a good question. Yes. Yeah. And then as the last example, I have 10.5, which is a very high CFL number. And here we see that all the other networks seem to diverge. And we also see that the 10, which has enough receptive field, still diverges in that case because, again, probably under the same argument. Okay, so this was the one axis of investigation, which was parameterization within one PDE. Let's now go to another axis of investigation, which is on architecture. And you already see it hinted here. There are going to be some colors soon. The first additional architecture is essentially, now it works, okay, is a convolutional ResNet. So it's very similar to convolutional architecture, but the difference is that they don't stack convolutional layers purely, but they also introduce some skip connections. You could interpret this as some Euler approximation to time integration, but I think the initial motivation for ResNets was primarily from an optimization perspective, that the gradient flow is better under these skip connections, and so that helped them train deeper networks. The second architecture I want to add is UNets, and UNets are essentially hierarchical convolutional networks. That means they apply convolutions on a hierarchy of different spatial representations. And I think that should definitely trigger multi-grid vibes. And there are, of course, a lot of ways to tune them. You can have different levels of depth. But the core idea is that, of course, if you reduce or interpolate down a state to a lower resolution, having a kernel size of 3 gives you effectively a wider receptive field, or physical receptive field. Or gives you, if you halve the resolution, it gives you twice as much receptive field. So they are designed around the inductive bias for long-range dependencies. The next architecture is another method to achieve long-range dependencies, is by dilating convolutions. In essence, here the idea is this is taken for 2D convolutions just as a representative image, but when we take the convolutional filter, which here is 3 by 3, and slide it across our image, we don't slide it like how we intuitively would, but we interlace or we skip certain parts in between. Dilated ResNets are a different, or dilated convolutions are a different way to achieve long-range dependencies, but oftentimes they are a bit different from units because units still tend to have better memory access patterns, but that's a bit of a detail, so it's just like another way to achieve long-range dependency. And the last is something which is not locally convolutional, but uses a Fourier spectral approach. So here use the Fourier node operator, and essentially its core idea is that we do a spectral convolution. It does some more to it, so for instance, it does not do spectral convolution across all Fourier nodes, it truncates some, but I think that's the core idea, that we don't have local convolutions, but work in spectral space. Okay, now with 4 architectures at hand, we can revisit the advection emulation problem, and now we basically add the green, the red, the orange, and the purple one. And in the first example of the low CFL number, we essentially see an interesting trend between the long-range convolutional architectures, here in red and orange, and the other architectures, specifically the short-range convolutional architectures, that those work not that well. And my interpretation for that is these long-range convolutional architectures, under problems which are local, right, it's a small CFL number, spend a lot of parameters on long-range interactions, which here are less crucial for achieving good performance. And so essentially a lot of the parameters are wasted, and that is what you also then see in their performance. On the other hand, the local convolutional architectures seem to work well here. We also see that the ResNet is a bit better than the convolutional network. That is because they are not like, they do have identical parameter counts, but here in that sense, the ResNet has an even larger receptive field, and maybe the additional skip connection additionally improved the performance, but I would say that it's still within the same class as the ConvNet. And then we see an interesting trend. We go to higher CFL numbers, and then eventually the long-range convolutional architectures seem to work, right? Which is also what is intuitive, because we need long range when we have high CFL number, and so we see that these networks then still work, and we see a linear error growth, which also indicates that they are not unstable for those problems. And then the FNO is an interesting special case, because its performance seems to be agnostic to the CFL number, which is because when we work in the spectral space, we are of course not limited by receptive field, and so the FNO's performance is not based on like the receptive field, but it is based on the spectral composition of the problem, and this will also become crucial in a second. Okay. Fix it. Okay, so basically now we have made 2 axes of investigation. So we parameterized an advection equation under different CFL numbers. We had the neural architecture, and now the third axis I want to discuss with you is on different PDEs. Okay, yeah, does work. Okay, great. So now we first have to talk about a general issue that you face when you want to benchmark neural emulators, is that how do you treat time? I would say probably the best way to treat time is, as I showed you before, I give you error rollouts. So we see how the error develops over time. We can see whether it becomes unstable. We can maybe also see if there is like an interesting trend that one architecture overtakes another architecture after some time steps. But of course, at some point we need to convey information, so you need to aggregate. So essentially what I did here is I ran all the emulators for 100 time steps and then aggregated the result. And the first problem is, or the first category I want to look at is linear PDEs. So we so far had the advection equation, which is the first order PDE in space. And I here look at the dispersion PDE, which is a third order PDE in space. So here the increased difficulty in contrast to advection is higher derivative. And in essence, we here have a similar configuration as before with the advection equation. So if there was like a CFN number for the dispersion, it would be here at around 4. So here we see that under this low quotation marks CFL numbers, the local convolutional architecture work well, and we have the long range not working that well because they have spending parameters on interactions not needed, and the FNO is somewhere in between. And then as the next, I now basically also go into 2D. So we now make some selected set of PDEs. Essentially, we go to a diffusion problem, which is a linear PDE. We are in 2D, and on top, I introduced, made the diffusion anisotropic, which means that it diffuses differently in the two spatial directions. And the core insight that we see here is that, again, since the diffusion was like set up fairly simple, so that we don't need long interactions, the short-range convolution architectures seem to work the best. Then the long-range convolution architecture follow. And then the FNO here is the worst one. There's an interesting insight here with the very bad error bar on the unit. I must admit I don't have a good explanation for that. It seems to be that under this configuration some of the unit seeds failed during training, and then of course the aggregation over the seed shows that. So essentially when you see an aggregation here, the bar plot is essentially the median out of in 1D 50 seeds and in 2D 20 seeds, and then the error bar is the 50 percentile. So in that sense that means quite a lot of seeds actually diverged. The reason the FNO does not work that well here is intriguing to me. I attributed that these spectral mixing or these spectral operations that the FNO does seem to not be that ideally suited for the anisotropy. That was my best interpretation for that. Yeah, that's at least the insight I got here. Then I went to 3D, and I call this n-balanced advection. That's of course like a bit of a real term. What does that mean? So it basically means that I have in 3D, I use an advection equation with a constant velocity, but the velocity is different per dimension. So that means unbalanced, and it's unbalanced in that sense that it is also different by orders, I think 1 or 2 orders of magnitude. And we see quite high errors here, so because in general, with 3D problems, a lot of other issues come in. So data management, so you have to reduce a bit of the data set size, and other issues also come into play. But I think we still see an interesting pattern here. So we still see that the short-range architectures do somewhat well, but the long-range now tend to work better, which is very interesting to me. I don't have a good explanation for that, unfortunately. But what I find more interesting is that the FNO does very bad here. And the reason for that is actually very clear, because when I set up these problems, I always use initial conditions with a certain number of Fourier modes being active, precisely the first 5. And we saw that the FNO works best, or the FNO's performance is dependent on the spectrum of the problem. And when you go from 1D to 2D to 3D, you need to tune certain aspects of your architecture. And especially the jump from 2D to 3D in terms of the parameters is quite significant. And so what I did for the FNO is I limited its modes or its truncation in the spectral space to 4 or 5, which is like very low. But here we see that the FNO doesn't work, which is kind of to be expected, right? If your state has 5 modes active and you can only handle 4, you will make a quite decent error in the 5th mode, and this is then displayed here. Okay, just a quick question. Should I already jump to a conclusion of the presentation, or should I, what do you think is a good timing?
I mean, you can take 5 minutes, 5 to 10 minutes, maybe not, well, a bit more than 5 as well.
Okay, great.
So as you wish.
Okay, great. Then I can talk about one more category, so which is nonlinear PDEs, which so far we have not seen yet. So here I added 3 different, so we have a 1D quadratic difference equation, which in the way I set it up is essentially using convection nonlinearity. It uses a dispersion term, and I made it hyperdiffusive. The reason the KdV equation needs to be hyperdiffusive is because we have a spectral method, and so we do need some source of diffusivity. I have the 1D Kuramoto-Sivashinsky equation, which is a chaotic equation, and the 2D Kolmogorov flow, which is a Navier-Stokes equation. And the trend we see here is that for the KdV equation, we see that the local and the global architectures work best. The ResNet is an interesting corner case. It is extremely strange to me why the ResNet does not work in this case. I also had it in some of the ablational studies that I had, that it did not work for the KdV equation, and I could not really figure out why that was the case. But looking at the other convolutional architectures, we see an interesting insight against the FNO here. So as I said, the FNO is like changed in a spectral composition based on the dimensionality. But in 1D, I think it has like 14 mode active. So that's quite a lot of modes. And the problem that we have with these nonlinear PDEs is that, as you know, that the nonlinear PDEs on periodic boundary conditions develop potentially quite rich spectra over time. And it turns out that if the spectrum is developing into something very rich, that at some point the FNO might struggle with that, or it needs more additional modes. But actually turned out if you bump the parameters of the FNO, so if you give it more modes, which requires more parameters, it also starts getting better again. But under a setting here, I think with around 30,000 parameters in one dimension, the FNO is not as good as the other architectures. And that's also true for the KS equation, which has quite a sophisticated spectrum in 1D. For the Kolmogorov flow, that's actually not the case, which is interesting. It's because I think the Kolmogorov flow here is set up at a sufficiently low Reynolds number. 1 second. And I guess that in this cases the spectrum is not too rich such that the FNO works surprisingly well, and maybe also the way the spectrum is formed is in favor of the FNO. Sorry. Okay, in the sake of time, I will skip the rest of the PDEs here. So just to give an overview, we looked at some reaction diffusion problems, and we did some investigation across dimension and resolution, but I will skip that for the sake of time. This, I think, is an interesting insight. So essentially, this is what we concluded from this wide range of experiments, that we essentially said that we categorized, which is like a rough categorization, into PDEs which are linear, then PDEs which are nonlinear and fluid-like, and nonlinear which are reaction diffusion-like. What is the difference? I think the important difference is that the reaction diffusion problems typically are defined by strong polynomial nonlinearities, so they have probably even richer spectrum than the one that are fluid-like. And then essentially, this is, as said, is a really rough categorization, is that if in the former two categories the spectrum is limited, the FNO is a perfect choice. I mean, it makes sense, right? It's a Fourier spectral method, and Fourier spectral methods work well for problems which are smooth, and the FNO is good for these smooth problems, so the FNO is a perfect choice. If that is not the case, we say that depending on the gamma and delta, so basically how difficult, or probably in other terms, how fast the dynamics are, or how wide the receptive field needs to be, we obviously distinguish between local and long-range convolutional architectures. And what we found, interestingly, across the long-range architectures is that the dilation mechanism works best in 1D, but the unit hierarchical mechanism works best for 2D and 3D. This is a bit of a high-level summary. I had one more ablation I could have talked, but I will skip that. Okay, let me summarize with, I just want to end with a bit of an overview on what APEBench is and some of the aspects we unfortunately didn't have the time to talk about. So something I briefly mentioned, which I think is very important, it is based on JAX. So JAX is a deep learning framework, and it enabled the fast solver, which was the basis for data generation, and data is the basis for training, and then of course they can be used as a reference. And one thing I learned from it was that since the simulation method is so fast, that also told me that the Pareto frontier that is created by the numerical methods that is out there is very far from what the neural methods can achieve, at least for the problems that I looked at. Which is also why I honestly told you in the beginning, the reason I did APEBench is not for pushing the Pareto frontier, because in this case, for these problems, I believe it's not possible. Or at least not with neural methods. I already said it has this fast simulator. We have the procedural data generation in seconds. It's actually even seconds in 2D and 3D, which is amazing. That's because these Fourier spectral methods are just crazy, in my opinion. We have differentiable physics. That's because of JAX. I did not talk about that much. If you want to talk more about that, I'm still here in the afternoon, and that's definitely an interesting topic to discuss. So in total, we have 46 PDEs. Like, since we have this parameterization mechanism, it's a bit hard, like what do you count a PDE and how's the difference? That's just to give a number here. I guess the underlying ideas we have a lot. Then we have a couple of emulator architectures, so the ones I showed you. I'm currently working on an extension with transformer architectures, which is also quite important at the moment. We have some unrolled training, which unfortunately I also did not discuss, but there are also some results on that. If you want to talk with me about that in the afternoon, feel free. I'm also interested in hearing your opinions on that. Also on neural hybrid emulation, which I unfortunately also didn't have time to talk about. Then you also in the beginning saw these nice visualizations with volume renderer. That's actually the work from my talented co-author Simon. He contributed the volume renderer, although it's of course like creates nice pictures that are nice to look at, but I think they also have some scientific value, because I guess these, when you work on 2D and 3D data, when you have a fast volume renderer, which works like in a second or a fraction of a second, you can get like immediately feedback on what is being created. It might not be the most precise as having a metric, but it is something which works extremely quickly, and I appreciated that a lot during the experiments I conducted. Yeah, and I highlighted it a bit. Unfortunately, I didn't have time to really put the strong point on that, but we saw it, for instance, with the similarities between finite differences and convolutional architectures, multi-grid and unit. We saw it with the FNO and pseudospectral methods. We see that certain properties or inductive biases that are in the emulators actually have similarities with numerical methods. And we, of course, get the features, but we also get the limitations. And I think that was something interesting I learned from that. Okay, the cool thing about APEBench is it is a pip installable package. So if you work on JAX, you can check it out. And there is also, I hope, vast documentation of it. And with this, I would conclude. Thank you so much for your attention. And we can have some more questions or talk also further in the afternoon. I will be here for a couple more hours. Thank you so much.